first. Okay, so what we are going to do is, I hope from last time, all right, I think you saw a little bit of what we are trying to do here in terms of the standing wave and what does it mean, right? In the nutshell, it's just by analyzing two waves that running in the opposite direction. And because we're talking about the sinusoidal waves, so there will be some conditions at some particular point that the medium itself will not travel whatsoever. It's sort of like standing still. So that's why we call this standing wave. All right. And because you have like a standing point, the point where things does not move as like a reference. So it feels like wave doesn't really travel. It's just like oscillating up and down. So it's come up when things, if you imagine in a string, when things go up and down quickly, then it presents itself as a loop like this. Okay. And now we understand from last time that the point where those mediums elements do not move, those we call them nodes. Okay, so those are the point where nothing is moving, and in between the nodes you can sort of like identify the position where things are oscillating the most, and that we will call them antinode. Okay, and what we learned from last time was like we know that the distance between any nodes will be just half of the wavelength. Or if you want, it will be exactly the same as the distance between antinodes because it's halfway between each other, right? Or you can imagine that if you complete one configuration, I mean, sort of like a representation of a loop. So one loop is also means have a wavelength as well. It depends on how would you like to pretty much analyze this thing. Sounds cool? All right, so let's sort of like give it a shot and see how it goes if you are asked about what is the sound that coming out from some sort of like an air column or a tube or something. All right, so let's give it a shot, and then I will draw this representation of the standing wave one more time along with you guys. Okay, so let's take a look at this. So it's like the question about this one is going to be pretty straightforward because now we know how to analyze the standing wave in a column. So let's take a look at this. A section of drainage covered 1.23 meter in length makes a howling noise when the wind blows across its openings. All right, so now we understand that every time that, of course, we blow, just like what I did last time, if you have a straw and then you blow on top of it, you will hear some sort of like, you know, some squeaking sound coming out of it in case of I have like a straw over here. But same thing will happen in any tube, any pipe, anything. And then if you have air blow in front of it or on top of it, then you generate turbulence in air. So eventually there will be some frequency or some wavelength that eventually give you those standing waves conditions. All right, and those will be the one that we saw from the simulation before that will give you the highest, you know, resultant waves. So that means those wavelengths that fit those conditions will be the ones that we can hear them the most. Does that make sense? Right, because you pretty much like send in crazy amount of, you know, sound, I mean crazy amount of wave vibration and everything into the tube, into a pipe, but the one that actually will sort of like get back to you, or at least after summations, after superposition, after combine all those possibility of waves that happens inside that tube, will only be the ones that can have the conditions met that has a large amplitude after the combination. So that's why you will hear those wavelengths the loudest. And the one that doesn't fit those conditions will pretty much disappear in the background. You won't hear that a lot. Sounds cool? Sort of. All right, so with this, so determine the frequency at first three, see? They say first three harmonics. It's not only one case, right? There are multiple possibilities that you can fit all these standing wave condition in here. Of the culvert, if it is cylindrical in shape and here, open at both ends. So we're going to try that one. So that means you're going to treat this culvert to be an open tube. like this. All right. And what we learned last time was like if you have both ends open, those will be location of the antinodes, because that will be the location where the air molecule should be able to oscillate the most. I mean, freely, right? You don't have any restriction on that oscillation. And here we go. This is the way to do it. You just have to make sure that you fit this condition, which is you start from antinode and you have to end on the antinode. So one thing that I can do is I can just, all right, here. That's it. I'm done. Okay, I just go from antinode to antinode, and everyone know antinode to antinode, you have to go through one node. So if I use that loop representation, it will look like this. So if you think in terms of a string, it's just going to go up and down, up and down, up and down, just like what we saw in the simulation last time. All right, so what you have over here is you have the node in between. And whatever you want to think, you know that the distance between antinode to antinode is half the wavelength. So you know that this is lambda over 2. But that is exactly the length of the tube. So you know that this easiest possibility of this one to occur is when L is exactly half of the wavelength. So you can say that the wavelength in this case is just twice the length of the tube. Cool? And once you get that wavelength, you can calculate the frequency by taking the V over lambda. That's just relationship between the speed of waves, the wavelength, and the frequency. So that's it. So it's a V over 2L, and you are done. Cool? All right. And then I can keep going, and now you start to see that I'm just sort of like reconstruct whatever the representation of those standing waves in the open air columns in the previous slide. So we'll do it one more time here. All right, try again. Consider the same tube over here. So what I can do next is, of course, the condition is start from antinode, ends on antinode. So I can do one flip. My bad. Here we go. Bam. There you go. See, I start from antinode. I am still end with the antinode. But here, I fit two nodes in between. So I have two nodes. So in between, see, the left end still antinode, the right end still antinode. So I must have an antinode in between. So from here, if you count, all right, or I mean, if you just measure or whatever. So what you have here is you have a perfect half the wavelength over here and another half the wavelength over here. Can you see this? All right. Or if you want to count the loop, if you like, you can say, hey, this is my loop here. And one loop is half of the wavelength. And you have another loop here. This is half of the loop combined with another half. So total is two loops. So it depends on whatever you want to call it, but that's fine. Two loops. That is 2 of lambda over 2. Or that's a lambda. Or you can just add this half of the lambda together. You get lambda as well. So what I have here is lambda is just the length of the tube itself. So what you get in this case is the frequency is just V over lambda is just V over L. Is it cool? Not bad. All right, and you can just keep doing this. All right, let's do one more because they said they want the first 3. They want the first 3. So I have to do one more of this. So I have 2 done. So let me have some more space here. All right, so let's do the third possibility is same tube right there. So what I can fit in now is just, I just give it one more twist. 1, 2, and 3. Here we go. 1, 2, and 3. See, I start from antinode, I end on antinode. But now I just squeeze in 3 nodes in between. So if you want to count, all right, you can start counting more time. This is 1 loop, 2 loop, half of the loop, and the half of the loop. So there are 3 loops. Right? Or you can just measure the lambda over 2, lambda over 2, lambda over 2, and then add them up. So at the end, what you have is 3 loops. And that is 3 times the half the wavelength. So that means, oh, okay, let me write it like this. And this is going to be equal to the length of the loop. So 3 loops are being fed inside this tube. So what you get over here is the lambda is just 2L over 3. And your frequency is just V over lambda. So it's going to be V over 2L. I flip 3 to the top. And that's it. All right, and this process just keep going and going. So I hope I just reconstructed whatever you just saw in this page. See, first, second, and third. Done. So that's what I think I try to go through this together with you guys. All right, and the better yet, I can actually rewrite this term to make it look like this. I just want to capture the pattern. See, the first possible frequency that you're going to get is V over 2L, right? But then the next one is here. V over 2L still appear on here, but then you have factor of 2 in front of it. And then in the third possibility over here, V over 2L is still there, but you have a factor of 3 on it. So now you start to see the sequence that is supposed to follow whatever you just did over here. That if you keep doing this analysis, you know that the next possible frequency will be 4 times that first frequency. And it's going to be the 5th times, 6th time, on and on and on. Cool? All right, so that's it. These are the dominant wavelengths.
Okay.
Does that make sense? So doesn't mean that there's no other wavelengths on these tubes. No. All right, all those wavelengths just go crazy in this tube, but still there. But these are the main dominant frequency or wavelengths that you are going to hear the most. And second of it is just like you have to think in another layer on top of this. This one itself, the first of the possibility, how can I say? Even though you said all these standing waves conditions are the dominant wavelength that you're going to hear, but among these dominants, the first one is still even the biggest influence in whatever you're going to hear. You see that it's like a double layers over here. You see what I'm saying over here? So these, like in this case, these 3 cases, or whatever that fits this standing wave conditions are the dominants. But among these, the first one is still the highest contribution of the sound that you eventually gonna hear from these two. Does that sound good? Good. All right. So it seems like it's, if you want to put like some intuition into it, it seems like it's easier for you to fit the low wavelength, the low frequency into the tube, because you don't need a lot of energy. You don't need a lot of fluctuation. You don't need a lot of oscillations. So this is supposed to be the easiest kind to make, or easiest kind that you probably have more sort of like higher tendency to generate inside a tube. So that's why we're going to name this. The one that has the lowest frequency, you can put like subscript 1 onto it, and you can name this one fundamental. Cool? Oh no, that's the wrong one. All right, so that's why the lowest frequency that you can generate inside this system is, we're going to call it a fundamental frequency. And because the second case possible, you have the factor of 2 in front of this fundamental frequency. So you say it's twice the frequency of the fundamental. You can put the subscript 2 on it. And we're going to call this the second harmonic, because it's twice the frequency. You start to see the naming scheme over here. And when you look at the third case, it's 3 times the fundamental. So you can put the subscript 3 on here, and you can call this the third harmonic. And that's it. That completes the whole explanation in this slide. Cool? I don't know if you call it cool or not, but it looks simple in the sense that it's just counting the loop or counting the wavelength, but underlying principle is just this. And it's pretty complicated phenomena to study, but once you understand it, I think it's not that bad mathematically. All right, so that's conclude. First harmonic, that's your fundamental. Second harmonic, that is your, you know that now. That's the second possibility that has the second, has the frequency twice as big as the fundamental. And the third harmonic, that's the one that triple the fundamental frequency. Cool. All right, and just to contrast this with another case. So let's take a look at the last problem that we're gonna face here. What are the 3 lowest natural frequencies? All right, so I throw in another word over here. See, you will see this one, and I'll just wrap up everything after this exercise here. There's so many terminologies that just pop up in the past lecture and today's lecture. So I just want to make sure that you sort of like captures all those terminologies that we are going to use. So over here, you have natural frequency, all right? But anyway, you just focus on frequency at this point. So find the 3 lowest frequency of the covert here if the block is, if it is blocked at one end. So let's say one end of this tube is being blocked. So that means you can consider this one as an one open and one closed tube, like this. Cool. And now what we are trying to do is, once again, we just subject this tube to the conditions. What condition is? The open ends of this one supposed to be antinode. And at the wall, the closed end of this one is supposed to be node because molecules cannot travel. The back is against the wall. So that is going to be the node. So that's it. So all you need to do is you just make sure that you fit this condition over here. Antinode on the left, node on the right. And what would be the easiest one that you can draw on this one? But the easiest one is you don't give any twist to it. Start from antinode, you go down to the node, and you're done. See, this is the easiest, or I mean, the one that you can simply draw it with your hands. And with this, then you can say, oh, Ajahn, I can see this is just the distance from antinode to node, or it's half the loop, right? It's not even complete one full loop. It's just half a loop. So each loop is half the wavelength. All right, or we know that the distance from antinode to node is a quarter of a wavelength. That's fine. So cool. So with that, we know that that is the length of the tube. There you go. So that means you will be able to figure out that the wavelength in this particular setup is going to be 4 times the length of the tube. So the frequency is just V over 4L, and you are done. And you can guess, but Ajahn, because this is going to be the lowest frequency possible you can fit in this tube, I'm going to call this the fundamental frequency. I put subscript 1 on it. Nice. All right. And you say, well, Ajahn, what are the higher frequency possible? You say, okay, just give it one more twist, shall we? So you just twist one more. So that means you just, all right, I'm just do one more twist on it. So with that, I introduce extra antinode and extra node here, which is fine. All right, so what you see right now is going to be, all right, I can see that this is a one full loop with half over the loop. So it's 1.5 loop. So it's 1.5. You can write it like a 3 half loop. There is going to be 3 half of lambda over 2. And that is 3 lambda over 4 is equal to the length of the tube. So that means this lambda over here is going to be 4L over 3. And your frequency is just going to be V over lambda. I flip 3 to the top and I'm done. Cool? Very nice. And, well, Ajahn, keep doing it. Put 2 twists to it. That is fine. Okay, and then you just count the loop, or you want to do the distance between or whatever. So this is 1 loop, 2 loop, and a half. So it's 2.5 loop. So what you can see over here, I can say is 5 half loop. So it's going to be 5 half of lambda over 2, or it's a 5 lambda over 4. And that's equal to the length of the tube. So with that, your lambda is going to be 4L over 5. Figuring out the frequency is going to be V over the wavelength. So I have 4L, I flip 5 to the top, and I'm done.
Okay.
And once again, because we have already defined the V over 4L to be our fundamental frequency, right? Now, can you see something here now? V over 4L shows up down here as well. So you can start to see that the next possible frequency that you can generate a standing wave over here is 3 times the fundamental, followed by 5 times. So that means in this particular tube, 1 open, 1 closed, you only get odd multiples of the fundamental. So speak in terms of the harmonic, because we say harmonic is just the multiple of the fundamental frequency. So that means what you should do in this particular setup is going to be, hey, I'm going to call this the third harmonic because it's triple the fundamental frequency. And I'm going to call this the fifth harmonic. Cool?
Okay.
All right, and now you can put the subscript everywhere you like if you want. So conclusion is, in the case of one open, one ends tube, you're only going to get odd harmonics of the sound coming out of the tube.
Okay.
So good. All right, and this pretty much summarize whatever you saw in here, and I hope you understand it. Yeah. All right, and as I said, I'm gonna conclude what kind of terminology that you have already heard. Let me put them all in here. So what you have heard today and from last lecture was just standing wave. So now we understand what are those. All right, what just the condition of two waves going in the opposite direction. You're figuring out the positions where nothing is moving. It looks like it's standing still. So that's why we named it standing wave. Okay. Second thing is those waves that fit the perfect standing wave creation, we can call it, it's create resonance in the tube. That is a resonance sound, resonance in this air column. So that's why it's sort of hand in hand, in the sense that when you speak of resonance, it means something is just in sync. You make the oscillation the biggest, or you do something great, very efficient. And that's what it is. Because we have already seen that you send in so many wavelengths into the tube, but these are the ones that shine. These are the ones that come out of it. So these are the very effective way of combining of those waves and other stuff. So something that is very, very sort of like obvious, very efficient, very good, and all this stuff, we call it resonance. All right, I'm just saying. Okay, so that's why these two goes hand in hand. All right, and we already learned about the harmonic. So harmonic, you think of it like a frequency. All right, and if you have the first harmonic, so the first harmonic is just fundamental. So first harmonic is equal to the fundamental frequency. And if you have the third harmonic, it means, okay, I know it's 3 times the fundamental. Okay, so you can think of the harmonic, it's just like the fundamental frequency if you want. I mean, it's a frequency, but once you put it into the first harmonic, so it's the lowest frequency that you can generate. Now I can throw in an extra terms if you like. This one just in case, because this comes after the fundamental. Sometimes you call this the first overtone. So there is a word overtone. It's like overtone is the next tone. So what I'm saying over here is, in this particular case, you have the first and the second overtone to be third harmonic and fifth harmonic respectively. Cool?
Okay.
So in contrast with the open end tube, fundamental is this. This is still the first overtone. So it doesn't matter. The next tone from the fundamental, you call it first overtone. The second tone above the fundamental, you call it second overtone anyway. All right. But for the open air columns, the first overtone is second harmonic. The second overtone is third harmonic. But here, the first overtone is third harmonic 3 times. The second overtone is fifth harmonic 5 times, on and on. It depends on the system. All right. But I hope you see the meaning of the word harmonic, which is just simply you think of the frequency, and overtone is just one next to, like you wanted to go like comparing to the fundamental, how many tone above the fundamental. And that's conclude standing waves, guys. Whew. Does that make sense? I don't know if I'm gonna call this make sense or not, but I think there's so many things that's squeezed into this topic over here. At the end, it sounds easy to do, easy to calculate, easy to draw the loops, the standing wave and all this stuff, and easy to count. You can count the loops to get to the wavelength. Once you get to the wavelength, compare it to the length of the tube, lead you to the frequencies. All right, but underlying principle of this one is not easy. It's still quite complicated. All right, just on passing, and then I hope just to make connections with this one a lot better. I don't know better or not, but I like this example a lot. So if I flip this one open, one ends tube upside down a little bit, make it look like this. Okay, so that means your fundamental frequency will go like this, right? That's your fundamental. And as I said, I sort of like noted that this is going to be the loudest sound that come out of it. So that's what exactly happened here. So if I have my glass of coffee over here, and then I dip my straw down into the water or whatever in the coffee in this cup. So this means the bottom end of this one is a closed end, and the top one is an open end. Does that make sense? So this exactly in the condition that I just draw vertically over here. So if I blow winds on top of this one, blow some air on top, you will hear that. Can you hear that? That is the sound. All right, even though you can hear a little bit that there's not only like a single frequency coming out of it, but the main one that you hear, that's fundamental frequency. Cool? And you can experience this every day if you fill up a bottle of water. You fill water into a bottle. Do you hear the that, I don't know, does that help or not? Right? Every time you fill water in a bottle or in a cup or in whatever, you'll hear this sound all the time. Like you hear that there is a sound coming out of it. It's getting higher in frequency. The pitch is higher. And now I hope you understand why. Because what you do when you fill up a bottle of water is you fill up the water down here. So when the water rising, right, getting higher and higher, what you get is the fundamental frequency getting shorter and shorter. Can you see that? See? So when the level of the water get higher and higher, you can see that everyone knows that this is going to be lambda over 4. And that is just it's going to be the length of the air column inside that bottle. So that means your lambda is just 4L, and that's F is just V over 4L. This is your fundamental frequency. This is the dominant one, the super dominant. This is the loudest sound that you're going to hear out of it. And that's the reason why while you are filling up that bottle, the frequency of sound coming out of it has a higher pitch as the water, water level reaching the top of the opening of that bottle. I hope this helped.
Okay.
It's I mean, you can play with it, or I can do the demonstration, but I mean, I tried it before. It's kind of pretty bad looking, so I think I'm just making the sound, and I hope you can relate to it. Or something like that. All right, guys. So that's it. That wrap up the standing waves right here, guys. Be done.
Okay.
Any questions? Sounds cool. Alrighty, guys. So that is it. So let's move on to the next topic, shall we? Alrighty. All right. So now it's time for the next handout. And I think this is about time. All right, guys. So we have arrived at the last slide before the second exam.
Okay.
So that means I think we're going to spend 1 week of this one. So it's been by the end of next week, we should be able to get this handout completely done. So we are approaching the second exam. So it's going to be pretty soon. So don't forget, I think we can ask you guys next week when we meet on maybe on Thursday that what we would like to do. All right. But I hope that you get the idea that the second exam will cover oscillation, waves, sound, and here optics. Okay, and what we are going to do today is going to be learn just a little bit of that optics first, and then I think we can finish it up next week. All right, that should be good. All right, so what I'm going to do today is just gonna show you what else in waves that we can study, and we're gonna learn a little bit of the law of the waves. That it doesn't have to be particularly for this, this particular type of waves, which is every time we talk about optics over here, we're going to talk about light wave now. All right. So we're going to use sound to study what we just studied in the past week. And we're going to use now the light wave to understand another types, another properties of waves, which is the reflection and refraction. All right, so those are the two things. All right, so before we get into those law, we would like to be able to describe waves in a different way. All right, so we move away from sinusoidal waves now because we know how to describe waves using mathematical functions. We know how to talk about the energy aspect of waves using intensity level, talking about the sound waves and all this stuff. During that time of study that's intensity, we forget, we don't have to worry about the sinusoidal function of it for a while. All right, it seems to be okay. And once we get back to the interference, then we bring back that sinusoidal functions, and then we try to do the combinations, try to add those two functions together to get to the form of the final standing waves function. Now, we're gonna be at the point where we don't need that sinusoidal function anymore. Isn't that cool?
Okay.
All right, we're gonna throw away that one more time because it turns out for these particular topics, we are now going to look at the traveling direction of waves. We just care about which direction it's traveling. Now we don't have to worry about the fine detail inside that waves anymore. Cool? So that means when we pay attention to just which direction the wave is travel, so we can just throw away all the detail and just care about which direction it goes. So that's why we are going to introduce rays. Rays is just, hey, think of it like it's just a pointing direction, which direction the wave is traveling. So look at this one. If you have a ray pointing to your right like this, that's easy. So it's a right traveling waves. So you don't have to worry about that fluctuation in here anymore. Okay, but then I can forget about it. And it's just talking about rays, even though you know that at some particular point, okay, inside of this ray, you know it's something is fluctuating. It's like sinusoidal waves or whatever waves, okay? And of course, perpendicular to this is still our wave front, just like before. We know there must be some oscillation going on, but we just don't care. So when we talk about this, now we still have extra problem, and allow me to talk about this briefly for now, right? And then we're going to take a break. We are not trying to push anything too hard, but the point is this. When you talk about the direction of wave, it is nice that waves travel in a single direction all along without any ambiguity. However, you probably have seen this scenario before. This is a top view of the water's wave. You can think of this like maybe it's the ocean wave. You look like top down onto the ocean, and then you see the water wave just approaching the shore, on and on. This is, I mean, it's just a water's wave. And then when you look top view over here, and imagine that if that ocean wave hits some opening over here, however, when the opening is big, you can sort of like imagine that the wave probably just keep traveling. Nothing has changed. That is fine. But now things get complicated when the opening of the wave is getting smaller. And you probably kind of like imagine that, hey, the wave that gets through that opening will spread out. Have you seen this before? I think you have noticed this. And that spreading out of the wave is even greater if the opening getting smaller. So it's spread out even more with a smaller opening. So what you're seeing over here is these two cases on the right. This is the one that we don't want to deal with. Why? Because if you try to represent the traveling direction, you don't know what to do here, right? Because it's spreading out. So your concept of rays, they're trying to help you indicate the direction of motion of the wave, kind of lost. It's kind of like, oh, I cannot use it anymore. I'm confused. I don't know how to split this arrow, right? So that's not good. All right. So that means all we care about is we are just going to look at the case where the arrows, the rays that we define, can be representing the actual traveling wave without any ambiguity. So that's why what we are learning right here, we're going to call it geometric optics. So we're just going to try to rely on geometry. We don't have any splitting. We don't have any wave function to deal with. We don't have anything. We only want to use just those rays. We just only want to discuss and analyze which direction the waves are traveling. And we're just going to use geometry to analyze. That's make our lives a lot easier. All right. And for this particular problem over here, that there is a spreading out on and on, this is called physical optics. This is physical optics. So it's optics that you need to bring back some formula, that you have to worry about interference of waves. You have to even introduce diffraction, the one that the wave can can use like diffuse out, can diffuse out. All right, we call it a diffraction. We're not studying that, so that's a good thing. So we're gonna try to tone down the material a little bit, so you don't have to worry about, you don't have to worry too much about that sinusoidal function anymore. Cool. All right, so that's what we're trying to do, is we're going to confine ourselves with just geometric optics, and we're going to rely on geometry, and that's hopefully it's kind of like make things a lot easier than calculus here. So look at this one. This is one quick example that eventually toward the end of this module over here, we will have a chance to deal with all this crazy stuff. But this is what happening here. You have, maybe you have some optical devices, you know, something. And as you can see, you only need to, hey, Bautan, I can use ray to represent which direction the light is traveling. It might have the directional changes, that's fine. But as long as you can still directly tell which direction the light is going with a little bit of deflection on and on, that is fine. At least you don't have any splitting, you don't have any curve, you don't have anything, everything is good. All right. And as you can see, you can, oh, all right, I can take a look at other, and this one goes on and on. So you can still draw the traveling directions with rays. Those are good. And we're going to rely on this purely to study optics of these lights. Cool. All right. So that's, I think that made your life a lot easier. All right. So I think this is just a good introduction of what we are about to do. So after the break, all right. So today is going to be light, once again, enjoyable Saturday physics. So I'm just going to pause here. So just have you guys, you know, set up things, you know, in your brain a little bit, and we'll come back and see at around like 15 minutes. So we'll see a little bit before 11. And I'm going to dive into the two laws of waves, or two properties of waves that we're going to use to analyze the traveling direction of waves. Okay. So, all right. See you after the break. Let's take 15. Yeah. All right. All right. So what we would like to study, I only ask, well, I would say only two properties of waves that we are going to study today. And maybe just one of them that you really need to do the calculation, all right, mainly. Because let's start with the first one. We call it the law of reflection. So reflection is law of waves. So that means it doesn't have to be light wave. It could be any waves. We already saw this one from maybe wave on a string. When the string hits the ends, the fixed end, it reflected back. Yeah, you notice that. Or if you look at the water's wave, when the water hit the shore, or water hit the wall, or whatever hit the rim and stuff like that, it's reflects, it bounces off. Okay, so the reflection is kind of obvious, it's there. But because if it's a light wave, then I think what you can see is you can see it by your eyes very easily. And plus, if you have like a laser beam, that make it a lot easier, just like this, see? So if you have like a laser pointer. So the good thing about the laser pointer is, I mean, the laser in particular, of course, it doesn't have to be the pointer. The laser is a unidirectional light. So whatever the light from the laser beam is traveling, you can imagine that beam of laser light to be the rays of that light, just like we defined over here. So that's nice. Yeah, so having a laser beam seems to be a very sort of like it's go really well with the concepts of rays. Okay, so if you have that, then this is what happened. When you have a wave reflect off of a surface, so you can think of it like that is a ray that coming in. So you can call this an incoming, the incident ray. Okay, now it hits maybe some interface or whatever, and there will be some reflection of this interface. So you call the reflected ray the reflected ray. So you call the ray that get reflected off from that interface to be the reflected ray. Now, to tell the direction of the incidence and reflections, what you have to do is, here, we make a measurement of the angle. Why not? Okay, but the only thing that's gonna, give you a little bit of like, okay, we have to agree with this, is you just have to draw a line that is perpendicular to that interface first. So we call this normal line. Okay, and just like this is like a convention. Our agreement is this: whenever you want to measure the angle, you make a measurement with respect to that normal. Cool? So that's why we can call this theta 1 to be the incidence angle. And things that happen on the other side, the refracted angle, is going to be the angle that you measure with respect to the normal line as well. Okay, and I think you understand why we would like to use normal line, not just the interface. But Ajahn, why don't we just use this horizontal line over here? You have to make sure that in reality, the interface might not look flat. And it will be so tough if you would like to use this flat line to be sort of like reference, because, oh well, of course, it doesn't point in the same direction all the time. Even though you can do it, but I think from the experience and from the usage and everything else, it turns out when you define the normal, it's easier for you to reference the direction of the interface better. Okay, so that's why we prefer to use normal line, but not the interface itself. All right, so with that, so from now on, every time you have a surface or you have an interface, then you draw the normal lines. And the incidence, the reflection, or whatever in the future you're going to have to analyze, you make angle measurement with respect to that normal most of the time. Okay, so with this, the law of reflection is very simple. And that's it. It says reflected angle must be the same as the incident angle, and you are done.
Okay.
It's easier. So that's kind of nice. All right, and that make it a lot easier when you have a very, very flat surface. So the good thing by having a flat surface means no matter which position of the reflection that's gonna happen, the direction of the reflected ray pointing in the same direction. So the good thing about this one is, whatever this light is representing, that representation of those things stay pretty much the same, even though it's a mirror image or it's a reflection. But you can still keep the shape and form of the original stuff that come in on the way out. So that's why we call this a specular reflection. Okay? And this is the reason why you can see yourself through a mirror or through a glass or a shiny surface and everything, because the reflection from of your face against, away from that interface, still keep the information about your face. Does that make sense? Right? Because all the detail about your face gets transferred to that interface and get reflected back. So you can still see your face of the reflection. So that's kind of nice. All right. And this in contrast with the reflection of the rough surface. Like rough surface, when you look around, I think you can look at like maybe your ceiling, maybe. I think your ceiling is not going to be a shiny ceiling. So with that, then the law of reflection works locally at every point. See, if it hits here, law of reflection still hold. If it hits here, then law of reflection still works. If it hits here, law of reflection works, right? So law of reflection works every localized position. However, when you zoom out, as a collective or as a macroscopic reflection, the roughness of the surface make the reflected beam pointing in all directions. So when you look as like a big picture here, you won't see a single direction in the reflection, but it's diffused because it's going all over the place. So in this case, you are pretty much lose all of the information that you try to bring in. Actually, I should draw like a better one here, like a triangle. And with the information that comes in, it's scattered out. So you won't get any of that information anymore. So that's why that triangular image that coming in, it just gets dispersed. So you won't see anything else. So that's why we call this a diffuse reflection. And you won't see the reflection of any rough surfaces. Yeah, sounds cool? All right, so that's easy enough for you. Okay, I can do this, something like that. There you go. All right, so that's classified two kinds of reflection, the specular and diffuse. Okay, and well, you kind of agree that every time that you want to see yourself, you need a shiny surface. So you can call like a specular reflection happens on the glossy surface, and the diffuse reflection happens on the matte surface, something like that. All right, okay. So with that in mind, now the second law that we would like to use, so reflection is done. Now the other one we call refraction. Here we go. And once again, just want to emphasize, it doesn't have to be light that has refraction. Any waves can do refraction. It doesn't have to be light. But it seems like light is the easy one for us to imagine what is going on. So what is the refraction? The concept is very simple. Look at this scenario, guys. So you can think in your head it's like a laser beam as usual. So you send in the beam, incident ray, hitting the interface. Now the interface is the interface between two type of medium. You can see up there is air, down here is glass. So now you are changing your medium. Okay, so it says, the law says, every time that waves try to go from one medium to the other medium with different properties, then there will be a refraction going on, going through the other medium. So that means when the light tries to travel from one medium, and then there is a change in the medium, the refraction will happen. And refraction, you can say, is like a bending. It's bent, it's turned, it takes a little bit of turn. Right? It might turn left, turn right, doesn't matter, but we're going to talk about what's kind of law that govern which direction is going to turn. But the thing is, every time that light change the medium at the boundary, there will be a refraction going on. All right? But the good thing about this figure over here, if you notice, that happens with the reflection sort of like tag along all the time. So what I'm saying over here is, every time that waves have to change the medium, it will generate, or it won't generate, there will be both reflection and refraction all the time. Here you go. Oh, wrong direction there. Okay, so there will be a reflection and refraction. Both will happen. And this is the reason why every time that you try to look through a glass window, even though the glass is transparent, but it's not perfectly transparent, you can always see a little bit of yourself reflected off from that glass, right? There's a faint reflection of yours, and that is because it's the change of the medium, air and glass, glass and air, on and on. So we'll do a detailed analysis on that, but that's the idea. So in conclusion, refraction is the bending of the waves when waves try to go from one medium to the other medium. Reflection happens all the time, every time that waves hit some boundary or hit some limitation or hit some, fixed point or whatever. When things is going on, there is some changes that's going on with the medium, reflection will always happen. Cool? All right, now let's come back to our business of refraction. So how can we determine the refraction direction? So look at this one. Once again, you have to draw a normal line, just like before. So you do the normal line, cut through that boundary in the perpendicular direction. So your incident angle is going to be this, this angle right here. That's your incident angle theta 1. So let me highlight this one. There you go. Okay. And now the outgoing ray, which is the penetration into the second medium, we call this, let's name this theta 2, it's going to be this angle right here. See? Measurement has been made with respect to normal all the time. So cool.
Okay.
All right. So with that, what is the relationship between the theta 1 and the theta 2? The incident angle and the refracted angle. It's following this law. We call it the Snails Law. And the law looks very simple. It says the product between n, I'm going to define it soon, with the sine of that angle stay fixed at all time. So that means if you know n of air, you take that, multiply by the sine of the incident angle theta 1 must be the same as n of glass, multiplied by the sine of the theta 2 according to this Snail's law relationship over here. All right, now, what is n, Ajahn? It turns out n is the ratio between the speed of light in vacuum, which is the highest speed possible in our universe, and the number is around 3 times 10 to the 8 meter per second. So that's a constant of the universe that cannot be changed. That is for sure. So C is right there. But now V is the speed of light in that medium. And one thing that you have to know is, it turns out, even though we learn from sound or mechanical waves, that every time that you have a medium for the mechanical wave to have a very high density, very tight, remember this wave on strings, remember that? When you have a high tension, the speed of wave increases, right? But not for light, because light is electromagnetic wave. There's no medium. It's electro, which is electricity, and magnetic, which is magnetism. So you don't need water, you don't need string, you don't need air, you don't need anything. It's the waves that does not need any medium to travel. So that's why it can travel the quickest when there's nothing in the way. So that's why the speed of light in nothing in vacuum is going to be the highest speed possible. And then when you try to send the light into some other medium, like in the air, in the water, in glass, it's going to travel more slowly because the light has to interact with the medium itself. Does that make sense? All right, so that's why we always see that V is always less than the speed of light, that's for sure. So that means the n that you're seeing over here is always greater than 1 all the time. The best that it can do is just equal to 1, which is the vacuum itself. All right, so hope that you now understand that n of the medium is just simply the ratio between the speed of light in vacuum, c, divided by the speed of light in that medium, and is always larger than 1. We call this n the index of refraction, or refractive index of that medium. Cool? All right, so that's it. So once n is being defined in this way, so there might be another textbook that try to write Snail's law in a different form, which is fine. You can just take the ratio of the sine if you want. So it's a sine theta 1 over sine theta 2 must be equal to the n2 over n1. Now you can apply this relationship over here because you can see that n is inversely proportional to the speed of light in that medium. So n2 over n1 is going to be equal to v1 over v2. Okay.
Okay.
So far so good. All right. Now you can still throw in, about I know v equal to f lambda. So that means I can also turn this ratio further into the ratio between wavelengths. That is fine too.
Okay.
Oh, that's wrong one. But then my question is, guys, can I just do this? What do you think? What's missing from this relationship over here is, what about frequency? But why you took the wavelength ratio but not the frequency ratio? The answer is, don't forget, we're doing physics. Something must be real. It's a physical world. When I say it's real, it's physical, think of it this way. If you imagine this is a light, or a wave on a string, or a water wave, or sound wave, doesn't matter. If you send in a pulse, that pulse must came from a disturbance, right? A real disturbance. So if it's a string, it's easy. Your hand has to move up and come down. So your hands really move up and down. This up and down movement of your hands send out the disturbance in form of the waves. But that means this wave already incorporate that information of your hands move up and down. And this is the fact that cannot be changed. You guys with me?
Okay.
Right? So that means if you move your hand ups and down in, let's say, in 1 millisecond. So within that 1 millisecond, it has to complete this movement no matter what. You cannot cheat. You cannot avoid this. So this is the reason why if you send in a train of a wave, that means you send in with some frequency. So it means every 1 second it has to cycle through, maybe like, you know, you send in like 100 hertz waves. So it means 1 second is going to oscillate 100 times. That 100 times per second has to be 100 times per second no matter where this wave goes. Does that make sense?
Okay.
So that means that frequency in first medium has to get into the second medium with the same frequency, because that is the fact. It's the physical changes that you cannot change. So this is the reason why we don't have to have any variation in frequency, because that is the one that is fixed. The only two things that are changing is either the speed or the wavelength. It has to compensate because F is already been fixed. So you got that one?
Okay.
All right. So I hope this clear things up about, because there are some questions before saying that about time, where did the frequency goes? Okay. And this is good in the sense that something has to be fixed. Otherwise, then our life will be crazy, right? Think about it. If you now can see, I can see that the speed of light are not the same in the air and in glass or in water or whatever in other medium. So that means, think about this. Imagine along with me a little bit, guys. So if you're diving under the water, okay, and your friends in the air send down, let's say like a green light. All right, you can still see that green light underwater. Why? Because it's a real green light. It's the same frequency no matter what. And good thing about this one is your eyes, your rod cell, cone cell, or whatever, your sensory nerves and everything react to that frequency. So that's why you can still see it looks like green, right? Even though the wavelength are not exactly as the same as the wavelength in the air anymore, okay? But you still see the green lights, right? If this is not the case, then yeah, it could be green above the water, and it could be, I don't know, red underneath the water, but things will go crazy.
Okay.
All right, but anyway, that is just emphasizing my point that waves has only single value of frequency no matter where it goes. Okay. All right. So that's conclude the Snail's law that is going to be used for the refraction of light. All right. So let's give it a shot here. So this table here shows the value of those n for some common material. Vacuum is 1. Air, actually you can approximate air to be around 1, because as you can see it's super close to 1 anyway. All right. Water, all right, this is 1.3 approximately. What else? Like typical clown glass is about 1.5 something. Okay, what else that might be interesting to you? Here we go. Sapphire. All right, so this one could be like a Swarovski or whatever sapphire stuff. Nice looking glass. And here we go. The biggest in this table over here is diamond. Actually, diamond is one of the highest index of refractions material that you can find in nature. And it's super duper high, 2.4, all right, for diamond. All right, so once we know these ends for many materials, now there are only two possibilities. You can have light travel from one end to the other. In this case, if you go from air to glass, now you look it up. Well, air, we can say is about 1. End of air is about 1. End of glass, let's say, is about 1.5. So that means in this case, you're going from small n to bigger n. So no doubt, according to Snail's law, the theta 2 must be smaller than theta 1. So in this case, you have the bending toward the normal. Can you see this? All right, the bending that is happening is toward, because if you extend the directions that initially the light is trying to get to, it's bent toward the normal line. So the opposite will go if you want to come from glass to air. So end of glass is about 1.5. End of air is about 1. Now you're coming from big N to smaller n. So in this case, you're going to have the bending away from the normal line. So the light is trying to deviate away from the normal when you're going from big to small index of refraction. See, there are only two possibilities right here. All right. But then it's going to go by how much. You just have to apply Snail's law. Cool.
Okay.
All right, that's not bad. Let's give it a shot, shall we? And you will see that this is a very easy breezy example over here. You have a layer right, strikes a flat block of glass. Given the end 1.5, the thickness of that one is given to be 2 centimeter. All right, so you have a block of glass over here, and the thickness is given to be 2 centimeter. Now at the angle of 30 degree with normal, so that's good. They already give you like the degree with normal line, so right there. So I can draw nicely one here. Yeah, let me say, hey, it hits 30 degree right there. Let me use red or green then. There you go. Bam. It hits 30 degree. And trace the light beam through the glass and find the angles of incident refraction at each surface. So what do you think happens at the location of contact over here? So just want to emphasize that when you want to apply the Snail's law, it's the application at the point of reflection. So as you can see, if it hits right here at the red dot, all you have to know, just collect all the information around that dot. Yeah, that happens, the refraction occurs around that dot. So the incoming is given to be 30 degrees with respect to normal. That's good. So n of this one, I can call this n a. Let me call it n a to be my n1, and that is 1. Cool. Now you hit a block of glass down here. It's going to be different n, so I'm going to use this to be n2, and that's n of glass is 1.5. All right, and now you just apply Snail's law. N1 sine theta 1 equal to N2 sine theta 2. Okay, and you say N1 is air, that's 1. Incident angle is 30, so you put 30 degree here. N2 is just glass. Now with this, you will be able to figure out what should be the theta 2, and you are done.
Okay.
See how easy it is to apply Snail's law. All right, but at least I can guess, because you're going from air to glass. It's small n to a larger n. So that means the refraction will happen in the sense that it's going to deviate toward the normal. It hits, particularly this case right here. You're going from air to glass. The deviation is towards the normal. So I can expect that, okay, if I extend this line out a bit, so I can expect that the bending will occur somewhere like this. Here we go. So the incoming will go like this, and it's gonna bend toward the normal with that theta 2. So if I zoom in here, let me draw this one. There you go. This is your theta 2. Cool. All right, now it turns out this ray itself eventually is going to reach the bottom interface. What happened there? Well done. It's going to look exactly the same here, because what I can do is, once again, I can draw my normal. See that? All right, and because it's theta 2 up there, so I know this is going to be my theta 2 as well. It's just opposite angle. So let me draw this one again. So we have two parallel lines, the dashed lines there. All right, and you cut these two dashed lines with a straight line. So theta 2 up there must be the same as the theta 2 down here is the opposite angle. So once again, you can apply Snail's law at the point of interface. So let me put a blue dot right there. Okay, so at the blue dot, you can write, now you coming from the glass, N2 sine theta 2. See that? Okay, and now you come out into the air, must be equal to NA again, so that's N1 is equal to NA. I mean, you can call this N3 if you want, all right, but equal to same one, and it's the same as air. Okay, so that's your third medium, but it's just air itself. So at the blue dot, N2 sine theta 2 equal to N1 sine, you can call it like theta 3. So what should be the angle that this light come out from the bottom interface? And that's it. You just substitute in. N2 is 1.5 again. Sine theta 2, you got it from the first half of the problem. N1 is 1 again. So from this equation, you will be able to figure out the theta 3. Cool? But if you look carefully บอกอาจารย์ wait n2 sine theta 2 is the same thing over here right
Okay.
and บอกอาจารย์ well I don't think you have to do anything because n1 is right there you come back to the original n so you know that n3 must be the same as theta 3 must be the same as theta 1 so that means of course you just go out 30 degree so that's it so that means it's gonna is going to deviate out from the normal but eventually it's going to carry on in the same parallel direction relative to the initial direction. Cool? All right, so if I extend that initial direction here, you will see that the outgoing ray will be parallel to the incident ray, but it's sort of like it gets shifted a little bit. All right, and this usually happens every time you have like a thick glass of a thick piece of glass or something, and then you see like a double reflection off from that thing because one is from the upper surface, the other one is from the bottom surface, but those two reflection is going to be off by just a little bit because of this deviation right here. Okay?
Okay.
All right, but anyway, the purpose of this exercise just to showcase how easy it is for you to apply Snail's law. Very cool. All right, try again, guys. Yeah. All right, this is more challenging one, and I think maybe the question in the exam will be somewhere around here. All right, not too difficult than this one, or it's just around here. Yeah. So when the rectangular metal tank in the figure is filled to the top with an unknown liquid, observer O with eyes level with the top of the tank. So let's say there's an observer try to observe something here. Okay, level. There you go. Can just see the corner. When you say just see the corner, what does it mean? It means the light that's come from the corner eventually hit the surface here and refract. And then once after the refraction happens, that light beam hits the eyes of the observer. So this is the reason why the observer can still be able to observe the corner of the tank, even though he just level his eyes with the surface of the liquid. Cool? All right. So in reality, it might not be exactly like this, but okay, in theory, it's doable. But in reality, you might have to move your eye up a little bit. Yeah. Okay. All right. But anyway, so look at this one. A ray that refracts toward O at the top surface of the liquid is shown. So the red rays that you are seeing here, that is exactly the beam of light that eventually hits observer's eyes. So look at this. If the dimension of these tanks are given, what is the index of refraction of this liquid? Can you try? Woo! What do you think? Well, Dan, that's no big deal because all you need to do is just apply Snail's law at the point of refraction, which is the green dots right there. So, all right, the normal line is already there. So just use that one. So your incident angle is going to be this. I can call this theta 1. So what is your refracted angle, guys? Well, Ajahn, that's it. It's 90 degrees. It's coming out into the air. So what you can see here is, let's say, n of this liquid. Let me call it just n. That's what we want to figure out. And the second medium over here, this is air. And we know n of air is equal to 1, right? So what I can do is this. I can write Snail's law like this. At green dot. Okay. So what you have is n of the liquid, sine of the theta 1. See, I'm working on the liquid in material right now. So I'm looking at the liquid n times sine of the theta 1, the incidence angle. Now I turn my attention to the air. The second medium is the end of the air. And now your refracted angle is 90 degrees. Got that?
Okay.
And that's it, guys. Sine theta 1. In air, I can set it to 1. Oh, sorry. I just want n. Let me move everything on the right side. So this is n. That's what I want. So n air is just 1. Sine 90 is also 1. I just divided by sine theta 1. So that means if I can evaluate sine theta 1, then I know what should be the index of refraction of this liquid. All right. And that can be done quite easily, because if you are looking at this triangle over here, you will be able to figure out the sine of the theta 1 is just the opposite over hypotenuse there. So it's the square root L squared plus D squared. Here we go. And because you know the dimension of this, L is given, D is also given. So because this is 60 and this 80, so I know this is going to be 100 centimeter. Cool. So with that, then I know L is 80 divided by 100. So I know what the theta 1 should be. And once I know the theta 1, or I know the sine theta 1, then I can just plug it back in. Oh, I don't even have to use the calculator here. All right, I can just plug it in. So that's it. So sine theta 1 is 10 over 8, 5 over 4. So it's 1.25, and I am done.
Okay.
Cool. That's not too bad. Am I doing trigonometric right, or my Pythagorean theorem is correct? Is it right? 60, 80, 100. Okay, I think so. All right. Okay, should be good. Isn't that nice? Okay, that's not too bad. So I hope that you start to see how to apply this whole thing. And if you have, like, you know, multiple interfaces, you have more than one or more than two medium, you just keep doing it. Because as long as you understand that to apply Snail's law, you just apply at a point of refraction. So things are going to be very straightforward. For example, like this. All right, with just this, I can tell you right away what is supposed to happen here. If you have a light beam, try to go from the top to the bottom. All right, they just want you to figure out the theta and the theta prime. One thing that you know right away from geometry, that you know this one's supposed to be 20 degrees as well. So I can say at the red dot, I can write it like this right away. NA, pay attention, at the top layer is going to be sine theta, must be equal to, look at the oil layer, the linseed oil layer. It's going to be N oil and sine 20 degrees. See that? And because they already given you the oil index of refraction is 1.5. So that's it. Sine theta is just N oil is 1.5. Sine 20, punch the calculator. N air is 1. So you should be able to figure out theta right away.
Okay.
Okay, and then you do the same thing with another point of refraction. Now you look at the bottom interface there. So you say at the green dot. Now you started from the oil to the air. I can start from the oil here. So it's going to be N oil, size 20. That's your incident angle. Must be equal to N water. Now you dive into the water. You want to figure out the theta prime. So it's sine theta prime. So from here, N oil is known. 1.5, sine 20 is known, and water is, now you go back and take a look at the table over here. Water, N is about 1.33. So you just put 1.33 here, and you will be able to figure out what should be the theta prime, and you are done.
Okay.
All right, so what's my point over here? The reason I want you to sort of like feel comfortable with the Snail's law is because it's so easy to use, right? And it's like you can think of it, this one is like a localized formula because it's a formula that you apply to a point of refraction. So that makes things a lot easier here. So what you can try with this is, here we go, guys. And this is the big one. And I love this phenomena over here. You can imagine now from the understanding of Snail's law, when you try to go from high index of refraction to a smaller index of refraction, the deviation is away from the normal, right? So you got that one, okay? Now, that leads to this. So imagine this scenario, guys. So you're going from glass to air. So you're going from bigger N to a smaller one. Deviation of the light is away from the normal, right? Here, look at this. You come in small, you're going bigger. You come in small, you going bigger, right? Because the deviation is away from the normal. So there must be one particular incident angle that the outgoing beam turns out to be at 90 degree. Oh, that's not good. Right? Because the refracted beam keep deviating from the normal line further. So there must be an incident angle that eventually makes the refracted beam go 90 degree. And that's kind of bad, because if you send in the light beyond this critical case, beyond this critical case, because this is a case that gets critical in the sense that if you send in beyond this critical angle over here, there will be nothing sent into the second medium anymore. Everything will turn into pure reflection here, pure reflection there. We call this phenomena total internal reflection. So this is a phenomenon that it's telling you that there is a critical angle. There is one particular angle that you don't want to go beyond this if you still want to get refraction. Okay? If you go beyond this, light will not penetrate into the second medium anymore, but 100% will get reflected back to the original medium. And this is the scenario that you can observe if you dive in underwater and you try to look up into the sky, but sometimes you won't see whatever on top of the surface of the pool, but instead the surface of that water acts like a mirror, just like this. See? And that is total internal reflection in effect right here.
Okay.
That's wrong. Sorry. Cool. All right. And that's it. That is good in the sense that, so that me and the time I can calculate this critical angle simply by set up the refracted angle to be at 90 degrees. That's all I care about. So that's it. So let me start from the first medium, sends in with the critical angle. So let me call it the theta C. C is standing for the critical. So theta C equal to N2, which is the second medium. And then I just set the refracted beam to be at 90 degree. Sine 90 is always 1. So that's it, guys. You can think of this as a relationship for you to figure out the critical angle between two mediums, N1 and N2. All right. And to make this possible, we already knew you have to go from bigger N to a smaller one. And that makes perfect sense for the value of the sine theta C. Because as you can see, to make this valid, N2 must be smaller than N1, because we know that the sine theta has the value less than 1 all the time. It never go beyond 1 or negative 1. Cool?
Okay.
That's nice. All right. So with that, what's the application of this? Well, of course, whatever the optical fiber that you use to send the information using light beam, that is the total internal reflection in the fiber here. Okay. So they use that core fiber to guide the light through that optical fiber. And here, this one on the left sort of showcase what is going on, but in reality it's not going like bouncing off like this. That's kind of weird. All right, but in the reality is they have to have some engineering in there to increase the efficiency, and the lights in there can stay in there more or longer without leaking into the side or away from the core fiber and all the stuff. So there are some techniques for them to generate a fiber that has an enhanced ability to send down the light. But overall, it will look more like, it's not going to look like a bouncing off like this. It's going to more like it's curved. It's sort of like it's trying to go in there and then, bounce off. Something like that. Because it has like a grading index of refraction. It's not like a single index of refraction fiber. It's a fiber that's being generated, having the index varies from the center of the core fiber to the rim, something like that. All right, and there are some nice, beautiful decorative items that utilize this optical fiber techniques and all this stuff. Yeah, it looks beautiful. Huh? All right then. So that's the whole thing, and then we use this for internet connections and everything every day now. All right, so the question that goes with the critical angle is going to be super simple in a sense that they will just ask you to figure out the critical angle. And don't forget, every time you talk about the critical angle, you have to you have to talk about two mediums, right? Because it's the refraction from one to the other. So that's why, look at this. If you send in the 600 nanometer lights, don't worry about the nanometer lights. Doesn't matter what lights send in, we use the same formula anyway. Find the critical angle of the following material surrounded by air. See, so they pair it with air. So you have a diamond and you have glass. All right, point is easy. You do sine theta c equal to n2 over n1. Yeah? This is, you can just do this formula. But personally, I don't even memorize this formula because it's just exactly the same as you start from. Okay, let me write it like this: n diamond sine theta c, right? Because you want it, come out of it, must be equal to out to where? Out to the air. And you just set the output or the refracted the output or the refracted angle to be at 90 degrees. All right, and that's it. You say, hey, so the critical angle is just in air is 1, sine 90 is 1, so it's 1 over n diamond. So it's going to look exactly the same as this one. N2 is air, N1 is n diamond. See? All right, so you don't have to memorize the formula because you know all you need to do, just set up the refracted angle to be at 90 degrees. Cool. All right, so with that, then what you have over here is you just plug in. You found in the table that the end of the diamond is about 2.42. And you just do the inverse sign. You will be able to get the theta c. Okay, you are done.
Okay.
And if I remember correctly, I think this is like about 424 or something. You can confirm this if you have time. Punch the calculator a little bit. But my point is this. If I do the same thing for the glass, so all you need to do is just follow the same step, and you will see that critical angle for glass will be just 1 over n glass. Yeah, it's a critical angle between glass and air. So that's why up top is 1, down here is n of the glass. And if it's n glass from the table, let's say it's about 1.5 approximately. Okay, and that leads you to theta c between glass and air to be, let's say, if I remember correctly, let's say about 42, 43, somewhere around there. Okay, and this is, I'm not sure. All right, but my point is this. Do you notice something from this result? What do you think? This is the reason why the diamond is sparkling. Got that one?
Okay.
Because it only takes 24 degrees for the light that enter the diamond to start reflected back. But if it's just a piece of glass, it will take up to 43 angle before light will start to do the total internal reflection. So this is the reason why the diamond, it's so easy for the light to get reflected back to yourself, the observer. So that's why you can observe the sparkling a lot easier than a piece of glass. And of course, plus the diamond, you can put the diamond cuts and everything on and on. You will make it even more sparkle and all this stuff. All right. And this is part of the reason why the shape of the diamond is always like this. I'm just drawing. I don't know exact, right. But it's not on scale or anything. But I see this. My point is that it's a fixed shape. All right. You don't have any like other angles of the diamond, because the reason that this shape is being chosen to be the shape of the most of the diamond is just because it's optimized for that critical angle. Right. That's why you call it like a diamond shape. It's unique because of that critical angle right there. All right. So you can cut, or you can come up with the same exact shape of the diamond but made out of glass. You won't get the shininess or the sparklingness of that, just like the diamond have. Okay, and you can do a little bit better with sapphire, like if you have like Swarovskis and all this stuff, because you saw from the table over here that the N for the Sapphire is higher than glass. So it's gonna be a little bit better, right? But nothing beats diamond. It's huge. Yeah, it's super, super, super duper big N right there. Sounds good? All right, so I hope this sort of helps a little bit. All right, guys. So I think what you can do with this is now, I think I want you to try these two exercises. I don't want to push too much because I think just want to make it light, and because I want you to try and have a chance to do this. And then I'm going to take the starting point of the next lecture to be, solve these problems together and use it as a review. So does that sound like a good plan? All right. So go back and maybe give this to a shot or think about this a little bit, and then I will work through these two problems together next time as a review. Okay? All right, guys. So any questions? Seems light enough today. It's kind of like easy Saturday physics here. All right, guys. So if there's nothing else, that is it for today. Thank you very much for sticking around. Bye-bye.